Right. So we had understood the definition of center of mass as a point about which the mass of a system is symmetrically distributed. So the general definition for center of mass for a discrete particle system which seen was the position of the center of mass was given as summation mass into position divided by summation of mass or total mass. So in other words, the position of the center of mass, it is the weighted mean of Ri, that is individual positions of the particles. So let's begin with another example. Four particles So very similar to a question we had done yesterday, but we had seen a two particle system. Now there's a four particle system. So for three of the particles, we've been given the position and the masses exactly. But for the fourth particle D, we do not know the mass and we don't know the y coordinate. The x coordinate is -1. So we have to find this y coordinate and the mass of D so that the center of mass of the system should be at the origin of the coordinate frame. Just try this out, people. We'll begin with this question. It's an easy application of the above formula. Okay.
Sir, I've sent to the answer.
Okay, so the y coordinate is -4/3 and the mass is 3m. Those are the correct answers. Darsh, Akshat, and Parv, all three of you got this correct. Okay. So let's understand, because center of mass and similarly summation m into y should be 0. So these are the answers. Okay. Okay. So now let us move on to the next aspect about the center of mass of a many particle system. We'll of course discuss about center of mass of continuous mass distribution also, but that will come later. Okay, let's first understand a little bit more about discrete particle system center of mass by understanding about motion of the center of mass. Okay. If at least one of the particles in a system like this is in motion, then there is a possibility that the center of mass is also in motion. Okay. Now I'm saying possibility because there's also possibility that the center of mass will not be in motion. Okay. So let's understand with example. So suppose we have a two particle system. Placed along our x-axis, and given that this is the situation at t equal to 0. So mass of A is, let's say, 2m. Mass of B is, let's say, 3m. Position of A is plus 3. Position of B is plus 8. At t equal to 0. Now after some time, okay, A has remained stationary. And B has displaced to a new position So we want to find the displacement of this system's center of mass. So what has happened is at time t, A is remaining here only, but B is displaced to some new position. So the center of mass would have been somewhere here, and now it's somewhere here. So you want to find the displacement of the center of mass. Yes, anybody got the answer?
Sir, is it 3 meter?
Yes, correct. Very good. The center of mass displaces by positive of 3 meters along the x-axis. Okay. So you calculated the individual positions of the center of mass at t equal to 0 and then again at time t, right?
Yes, sir. Yes, sir.
So see at t equal to 0, you can see that the center of mass, it is at xc equal to this kind of formula now. Okay. So it's located at six, right? And now at this new time, yes, there is another method we see, especially, if there's a, instead of a two particle system, this was a many particle system, and many particles had displacement, not just B, then this would be a very cumbersome method of calculating the displacement. So we will develop a more streamlined formula for it. Okay. From the definition, from the kinematics definition of displacement, we'll develop a formula. Okay, so now let us discuss the general formula for displacement of center of mass. So let's understand how this works. So we'll take a more fundamental approach here. Okay. So we know that in general, displacement is equal to change in position, or displacement during a certain interval of time is the final position minus initial position. This is the definition of the displacement object or whatever, right? So therefore, the displacement of the center of mass should be nothing but change in position of the center of mass. So using this definition, we can see that displacement is the change in summation mr divided by summation m. Okay. Or you can say it is delta of this quantity is kind of a summation and this kind of summation in the denominator. Okay. Now, next thing we'll do here is we'll operate this delta on the system, and when we do that, we'll see that the individual masses are not changing. It's only the positions which might be changing, because the system might be in motion with more than one particle in motion. So when we operate this delta inside this term, it becomes the denominator is a constant, so we just let it be. And in the numerator, it becomes summation mass into change in position. Or it becomes like this. Okay, so one step further. Now, delta of R is the individual displacement for that particular particle. So the displacement of the center of mass has a similar formula. It is the weighted mean of the individual displacements. Okay, so now you see, if you apply this definition to the above question, we can do it in a more direct manner. Right, Parv? That example we had taken, you can see that. In that example, what was happening was that this particle of 2m was remaining stationary, but this particle of 3m, this was moving from here to here. It had made a displacement of 5 meters. Displacement of center of mass. This would have been 0, but this would have been 3m into 5. Okay, so this is a more direct way of doing this type of a question.
So can you scroll up to the question for a second?
Yes.
Okay, sir. Done. You can scroll down.
Okay.
Done, sir.
Okay. Now, next thing from this we'll understand, just like we have defined displacement of the center of mass as weighted mean of the displacement of the individual particles. Now, next thing we can also define velocity in the same manner by using the definition of velocity. So in general, velocity is defined as rate of change of position or rate of change of displacement. So here, velocity of the center of mass is the instantaneous rate of change of position or displacement. Okay, so I'll write the result directly, but I want you to try and complete the steps yourself to understand that the velocity will become the weighted mean of mass into velocity divided by total mass.
Done, sir.
Okay, so understood this now?
Yes, sir.
Yes, sir. Understood.
Okay, now before we move on to examples and also about acceleration of center of mass, from this definition of velocity of center of mass, we also get the definition about momentum of a system, how we define the momentum of a system. Linear momentum of a system of particles. So in general, we define momentum of a particle as mass into instantaneous velocity. Okay, this is linear momentum of a particle. A body or object or whatever. Okay, so linear momentum of a system is defined as its total mass into velocity of the center of mass. So capital M over here is the total mass, summation M. Okay, so now if we apply this above formula, we can see that so the total momentum of a system, which is mass into velocity of the center of mass, is also equal to summation of mv. Of the individual particles. So this is how we define momentum of a system. Just make a note of this, people.
Sir,
Yes.
sir, can you just explain the second last step that to do?
Okay, so momentum of the system now is mass into velocity of center of mass. Okay, that's what we've written in the first statement. P system is m into VCM. M
Yes,
is total
sir.
mass. Now we are just substituting the definition of VCM, okay, from the formula above. So we'll replace velocity of center of mass with what? Summation of mv for the particles divided by summation m.
Yes.
Understood now?
Done, sir.
Okay. Okay, so we can also write this like this, that momentum of the system, therefore, which is total mass into velocity of center of mass, is also equal to vector sum of the individual momenta of the particles. Also define it this way. Okay, so let's understand this with a example. So let's say we have a two-dimensional coordinate frame. We have an XY plane. And we observe certain particles in this XY plane to be in motion. So this system center of mass just a second. Yeah, so this system center of mass is somewhere over here, let's say. It's having some kind of a velocity. So find the velocity of the center of mass. So let's understand this example. Then we'll move on to acceleration of center of mass and also something important, which is called the impulse momentum theorem for a system of particles using the above definition of momentum.
So can you check my answer?
Okay, so I'm working out this question to verify your answers, Akshat. So what we have to do is first express the velocities of A, B, and C in vector component notation. Okay, right now it is given in geometrical sort of notation. So it will be easier if we first express these velocities in the I cap, J cap kind of notation. So you can see that velocity of A is 4 I cap plus 3 J cap in meters per second, because VA has a magnitude of 5 meters per second and theta is equal to 37 degrees with respect to x-axis. Velocity of B we can see directly is minus 3 I cap, and velocity of C we can see is plus 2 I cap. All in meters.
Minus 3 J cap.
Yes, minus 3 J cap. Correct. Okay, so velocity of center of mass is going to be a formula like this now. I mean, the general formula is like this, but here it will become arithmetic mean because the masses are equal. So here this will become VA plus VB plus VC by 3 because this is given to us. Okay. So hence, you can see that velocity of the center of mass will become, so 4 plus 2, that is 6 I cap plus 0 J cap divided by 3. So it is plus 2 I cap. It's 2 I cap or plus 2 I cap, whatever. So now we can make a correction in the diagram and show the direction of the velocity vector of the center of mass. It is going to be along the positive x-axis. It's going to have a magnitude of 2 meters per second.
Done, sir.
Hmm. Okay. Exactly, but so see, center of mass is ultimately a point, no? So if it is a point defined for a system which has distribution of mass, so if that system is in motion, then that point will be in motion along with the system. So obviously it will have, you know, displacement, velocity, acceleration, etc. Because those are parameters related to motion, right? So if a system is in motion, its center of mass is a geometrical point within the system, and that point is also in motion. So it will have all these parameters related to kinematics. Whereas you can't say, for example, that the center of mass has momentum, because momentum is a property of the system, right? It's a dynamical property, mass into velocity. So it's the total mass into velocity of this center of mass.
Okay, sir.
So it depends on what type of property we are talking about. So whether that property belongs to the whole system or just the center of mass as a point. Okay, so accordingly we have to define. Okay. Now coming to impulse momentum theorem, next thing we'll see, that is directly as a consequence of the definition of momentum of the system. So we had just seen above that momentum of a system as a definition was equal to its total mass into velocity of the center of mass. But we had also seen that momentum of the system is summation of individual momenta of the particles. So from this, we will now apply the impulse momentum theorem by differentiating both sides of this. So rate of change of momentum of the system, which we can define as rate of change of total mass into velocity of center of mass, that becomes rate of change of summation of momenta of the particles. Okay. So rate of change of momentum of the system is equal to total mass into acceleration of center of mass. Okay, because here all the individual masses are constant. So total mass, which is summation m, is also constant. So it is what we call a fixed mass system. So in such a situation, that becomes equal to summation of this. Now next thing we'll see, by Newton's second law, rate of change of momentum for the ith particle is the net force acting on the ith particle. and summation of net force on all particles will become the net external force. On the system. Why? Because when you sum up all the forces on the particles, the internal forces to the system will cancel off in action-reaction pairs. Only the external force will survive in the summation. So this is a net external force because on summation of Fi, that is the net force on all particles summed up, the internal forces in action-reaction pairs cancel. So that is why summation of all forces just equals to the net external force. Okay, so just write down up to here first, then we'll discuss. Okay, so because of Newton's third law principle that every action has an equal and opposite reaction. So when we sum up all the forces acting on a system, the internal forces are there present in action-reaction pairs. So they have to cancel. So you're left with the net external force. Okay, so now coming back to the earlier statement that rate of change of momentum of the system is equal to summation of rate of change of Pi. Okay. No, so external forces are the vector sum of all the forces acting externally on the system. Acceleration is the effect, beta. Force is the cause. Okay. So whatever external agents are applying forces on the system, if there are multiple forces, then we have to sum them up, and that is the net external force. Okay. So now from this we can see that the net external force on a system becomes equal to the rate of change of momentum of the system. Because of this. So this now implies this statement. So this is Newton's second law. Applied to a system of particles. When you apply it to a single particle, we say that the net force acting on it is equal to the rate of change of momentum. When we apply it to a system, we say the net external force, because the internal forces have to cancel in action reaction pairs. So the net external force on the system is equal to rate of change of momentum of the system. So the system has a constant fixed mass, capital M. Then that becomes equal to the total mass into the acceleration of the center of mass.
Done, sir.
Right.
That's
Okay, so now we can see that if we just cross multiply the terms in this equation, this last equation, okay, so from here we can see that the net external force into a time interval dt is equal to change in momentum during that time. So we integrate this now. During a certain time interval. So this becomes the change in momentum of the system during a certain time interval is equal to the impulse due to the net force, the net external force. Force integrated over time, as you know, is the impulse due to the force. So this statement is like the change in momentum for a system in time t equal to t1 to t2 equals to the impulse due to the net external force. The given interval. And therefore, this is called the impulse momentum theorem. Also write it like this, that the change in momentum of the system equals to the impulse due to the net external force. Okay. So this is the impulse momentum theorem. For a system of particles. So impulse is a general definition, beta per, whether it is a short interval or a large interval of time. For example, if we are continuously applying a force for significantly long duration, then the impulse is the integration of that force over that long duration. If it's a constant force, it will simply become force multiplied by time.
Okay, sir.
So what you have written in last, delta P system is equal to
J, capital J. Capital J is a symbol used for impulse. Okay, now one very important implication of this now is that if we have a system on which the net external force is zero, the momentum of such a system is conserved. Okay, so in such a case, we will apply conservation of momentum or conservation of linear momentum to solve the dynamics of such a system. So that becomes an important special case of the above equation. If the net external force on a system is zero, okay, so this term only is zero. So the impulse, which is that net external force integrated over time, will also be zero. So that means the change in momentum of such a system will be zero. So that means the momentum of the system is constant. So if the net external force is zero, that means the momentum of the system should be constant or conserved. So that means velocity of the center of mass is uniform. So we apply the principle of momentum conservation. For a system which is isolated, meaning that the net external force is zero. Yes, if net external force is zero, then momentum will be conserved. But the way we express the conservation of momentum will become somewhat different. Okay, because if mass is not constant, then momentum being constant does not mean that velocity of the center of mass is uniform. So we will come to that per separately in a section called variable mass systems. Okay, but at the moment we are applying this definition to a system of particles which is of uniform or constant mass, not of variable mass. Okay. So let's look at some examples of momentum conservation. So like if we have a situation like this, that we have a frictionless surface. This is a smooth surface. Now on this we have placed two blocks which are initially at rest. Blocks A and B. Now this, they have some charge. So A and B have mass m and 2m and charge some plus q1 and plus q2. So initially they are placed at rest, but then they start repelling each other. Placed on the surface and released from rest at t equal to 0. Now after some time, due to mutual repulsion, electrostatic that is, they have displacements and velocities so we have observed the same diagram after some time. Let's say this is where they were initially. But by now what has happened is that we made some displacements like this. Okay. So if VA is equal to 2 meters per second, find BB. And if displacement of B is, let's say, 2.4 meters, find the displacement of A's magnitude. Just try out this question, people.
Done, sir.
Okay, so people, let's complete this problem. So here what we'll see is that the net force on the system is 0 because there is only mutual force of repulsion between them. So that action reaction pair cancels. And other forces like normal reaction weight, etc., they cancel each other. So the net external force on the system is 0 because this electrostatic force and this electrostatic force, they cancel each other. Okay. So that being the case, now here you can see because the system started from rest, so velocity of center of mass is 0. So here also the velocity of the center of mass should be 0. So if this is having a velocity Vp like this, so So applying the momentum conservation principle, and since velocity of center of mass is 0, so displacement of center of mass will also be 0. So mass into A into displacement of A plus mass into B into displacement of B should be 0. So again, okay, so people, with that we complete today's session. Okay. So plenty of questions in H.C. Verma's first part of system of particles chapter to do with position of center of mass and simple linear momentum conservation and velocity and etc. like this. You can start with some of those questions. Next week, one of the sessions we can keep for discussion of any pending doubts and questions. Okay. So that's it for today's session. People, wish you all the best. Have a nice day.
So
Yes.
I have a doubt.
Yes. Tell me.
So what's the logic behind this thing that like charges repel and unlike charges attract?
It is the nature of charge, beta. Electrostatic force is one of the fundamental forces known in nature. Okay. And that is the nature of charge, that you have two types of charge, positive and negative, and like charges repel and opposite charges attract each other.
So but that we have made the convention like
No,
that.
we have not made the convention, but that's the way the fundamental force of electrostatics works in nature. It's one of, that's the thing. It's not a derived force. It's one of the fundamental forces.
Oh, okay, sir.
Okay.
Thank you, sir. Bye, sir.
Okay.
Sir.